Welcome to 1010 Analytics. In this video, we'll be talking about what is underfitting in machine learning, why underfitting can be bad, and some practical approaches for dealing with underfitting and high bias, and also some algorithm-specific approaches for dealing with underfitting. So what is underfitting in machine learning? Underfitting happens when a model learns very little from the training data, and the model is just too simple, not complex enough. This can be detected if model performs poorly on both the training set and the testing set. So for example, if you choose accuracy as your chosen metric and the model shows 15% accuracy on the training set and about 20% accuracy on the testing set, you can say that it does poorly everywhere. So it does not detect the pattern anywhere. So in the image below, you can see overfitting happens when the model learns too much and all the noise is captured. It's fit too perfectly. Underfitting is when it essentially does not learn anything. And a good balance would be when you're able to understand the underlying pattern and you're able to ignore the noise and random fluctuations. Now, why underfitting can be bad? It can be bad because it can negatively impact performance of model on any data, because it will just not be able to capture the underlying trend of the data. And an example I used in my previous video about overfitting is that a child is trying to learn what a tree looks like, and only oak trees are in the images of the training set. So if it's underfit if the child concludes that anything that is green is a tree, which is too simple. And it could be overfit if the child concludes that a tree is a tree only if it has similar height, width, leaf pattern, branch pattern, and any other distinguishing features just of oak trees. So for example, if you give the child an image of a willow tree, a maple tree, or a pine tree, the child would say that that is not a tree at all, because it does not have the same specific height, width, or leaf pattern, and that is overfitting. And a good fit would be if something has leaves, branches, and trunk could be considered a tree, and that's not perfect, but it could be good enough. Now, one practical approach for dealing with underfitting is dimensionality addition. So remember, in my previous video I discussed about overfitting, where dimensionality reduction was one way for dealing with overfitting. For underfitting, you're trying to add dimensionality. You're trying to increase the dimensionality of the feature space by selecting more features. And as the degree of input features increase, as the degree increases, the model complexity also increases. So one way to do this is through feature engineering. This is very important in data science. So we try to use domain knowledge to modify existing features to get meaningful information and try to capture as much insight as possible. Some ways for doing this is you can engineer labels of categorical variables through one-hot encoding. You could create mixed variables. You could engineer dates. And you could do feature scaling like standardization or min-max scaling. And you could do Gaussian transformations. You could also do discretization. So all these are different ways of engineering new features by modifying existing features. And then you just add these additional features to the model. And another way for trying to mitigate or trying to prevent underfitting and overfitting together is cross-validation. Same thing was said in my overfitting video. And you can use k-fold cross-validation, where you divide the training data into k number of subsets. So if you take k equals 5, then you'd use 4 sections as training set and the remaining 1 as a test set. And you'd repeat this until every subset has been used as a test set once. So you'd repeat this 5 times, and then you'd average the error estimation over all these 5 trials. And another way is through leave p out cross-validation. So here you leave p number of data points out of training data. So you select P as 20, and you've got 1,000 data points everywhere. And so you'd got 20 for testing and 980 for training. However, you'd have to repeat this for every single possible combination of 20 data points, which would be huge. So one computationally less expensive way of doing this is by selecting P as 1. This is called leave one out cross-validation. So out of 1,000 data points, you'd select one as a test set, one data point as a test set, and you'd repeat this 1,000 times to get through every single data point as a test set. Now let's look at algorithm-specific approaches for dealing with underfitting. So if you're working with linear models and you've applied a regularization term, then you'd want to reduce the amount you've regularized it. And if you're working with artificial neural networks, you could potentially increase the amount of hidden units to increase complexity. And you could also decrease regularization to increase complexity. And if you're doing k nearest neighbors, you could potentially decrease the value of k if you've got a large number there. So for example, if you've got k equals 100, then you're looking at 100 different neighbors of every data point, which could be too general. So if you reduce it to like 10 or something, you'd only look at 10 nearest neighbors for each point. And if you're using decision tree algorithms and you have pruned your data, and you have already pruned your decision tree, which means you've shortened it by reducing different sections of the tree that provide little power to classify, then you might want to stop reducing it too much, or try to not prune it at all if it's underfitting. And all right, that was a pretty short video. And if you found this video helpful, consider subscribing to the channel in case I upload new stuff that you might find interesting, that might catch your eye. Thank you very much for watching.